This video is a continuation of the Scalar Theory of Everything video. It is about the big, that is, about cosmology. The previous episode of the CNPS had the introduction to the Scalar Theory of Everything on 17 February. This is a link to that video. The STOE is concerned with ontological reality and causality first, then math to describe reality and causality, and then only sufficient math to make predictions. Let's start this video with a little introduction about how I'm going to talk about the cosmology. And I'll do this by an example of how we can rephrase Newton's laws to show the difference between transformation and mapping concepts and measurement and calculation. So to start, you'll note that you measure distance between bodies and ticks of a process which is assumed to have a constant duration, a clock. You calculate acceleration as a first order effect. Then you map, which is a mathematical operation, the calculation to a fictitious, not ontologically real force called inertial force. To do this, you apply a constant of proportionality, here we're going to call it MI, called the inertial mass of the body. We can also postulate another fictitious force, here we call it Fg, called the gravitational force, which is how the body influences or causes changes in the plenum. And this is action by contact with a real plenum. The plenum change is propagated throughout the plenum. That's the nature of the plenum. It propagates waves. The gradient of the plenum acts by contact with the surface of hods. Remember, this differs for photons, where there's one surface direction along its perpendicular to its axis. For neutrinos, there are two surface directions, and for baryons, there are three surface directions. Then suggest that the F's, our vectors, are proportional, that is to say, are related by a proportionality constant, which is called the big G, or Newton's gravitational constant, and the body characteristics, Mi and Mg, are assumed proportional, and they become part of the G, of course. Then note the plenum between them obeys the spherical principle. That is, the big G includes three proportional constants, Mi, Mg, and a distance relation constant. The motion, which is what is observed, is obtained by inverse transforms. You'll note here we're talking about forces, not energy. So in general relativity, we take a measurement. This creates forces. The forces then over distance and time are energy and momentum. The space-time gradients, which is the mapping, change in energy, and these then produce changes in the world line of bodies by the inverse transform. Or in the STOE, we measure relative distances of bodies, which then gives you the plenum changes. These then cause forces or gradients in the plenum acting on bodies, and these by inverse transform causes changes in the motion. So the plenum is somewhat analogous to space-time. Physics has three general kinds of creation myths. The Big Bang, of course, where the universe had a beginning, then matter condensed into galaxies. The Quasi Steady State Cosmology suggests the universe is eternal with expansion or with cycles of expansion and contraction. And then we have the STOE creation myth, which doesn't really say much about how the universe came to be. The universe may or may not be eternal. And it has cycles of temperature increase, which is expansion, and decrease, contraction. Now, the STOE philosophy here is that we have a sphere of things that we can measure and understand, and another sphere of somewhat we can predict. And outside of that sphere, we really can't say much except by hand waving and very spiritual type arguments. The Big Bang suggests all particles have a world line, and that's what you do is you track the position over time with one time and place of creation. The quasi-steady state cosmology has a world line of particles, but the particles are created in the universe over time. That is to say, the quasi-steady state cosmology introduces a creation field, uppercase C, a scalar at center of all galaxies. That's going to be important in a bit. The STOE adds to the QSSC particles also have annihilation, that is to say, a termination of their world line at sinks in elliptical galaxies and sources in spiral galaxies. Sources and sinks in the STOE allow the universe model to be finite and bounded. Annihilation of particles out of our universe is not a new idea. Here's a paper in 1994 that suggested annihilation, but their annihilation of what they had to do to satisfy the equations they were using, general relativity field equations, still had problems. That is to say, the source and the sink had to be kind of close to each other, and the dust was in intergalactic space, but intergalactic space is relatively transparent. And this is why the STOE abandoned general relativity field equations. The reference for the QSSC is here. It's a different approach to cosmology. The QSSC also uses general relativity field equation. Here you see the normal right-hand side with the cosmological constant, this thing, on the left-hand side. On the right-hand side, we see the gravitational constant and, of course, the stress energy tensor. And here Narcalar adds the creation tensor, where the creation tensor is a scalar field which arises explicitly from mass world lines at the beginning of the particles, i.e., when there is creation of particles. Or in the STOE, we add annihilation in the STOE as part of the C. The left-hand side you see here is the mapping. And this then is not real. It's a mathematical mapping. Take note of where the cosmological constant is. In the QSSC formulation, the thing that stands for relatively dark energy, the cosmological constant, is on the unreal side. It's the mathematics. You'll see in some statements they'll put this thing on the right-hand side, meaning that they're suggesting that the dark energy is real. Here, in the QSSC, this is the creation, so we don't need dark energy, except as the mapping. The left-hand side is the geometry of space. Note geometry, and this is what Riemann does. He takes and eliminates one constant on the right-hand side by making it geometry on the left-hand side. Is it a real component of the universe or a mapping? We're suggesting here that it's a mapping. If you consider it a real component, then it indicates that the maximum speed allowed for light is c. And this conflicts with entanglement, Coulomb speed, and gravity speed, as noted in the first video. Therefore, the left-hand side is a mapping. It is not real. Before about 1990, the steady state idea of Hoyle considered the creation of particle world lines to be in intergalactic space. This idea was rejected. The last rejecting observation was the uniformity of the microwave background radiation. Then the creation site was changed to be at the center of galaxies, and this became the QSSC on the right-hand side of the field equation. You note the dark energy term is on the left-hand side, as we noted before. In the QSSC, there are many creation events, and Nargalar has been writing papers over the last decade or so about these many creation events at the center of galaxies. These many creation events cause the creation of world line of particles, or hods, in the STOE. The STOE adds another constituent of the universe, the plenum, and so hods and plenum are both real. The plenum being real is one of the issues which the STOE has to deal with. This creation and subsequent nucleosynthesis, that is to say, combining the hods and plenum to form particles, causes the outflowing of bodies and plenum from spiral galaxies' center, and which resolved many observational issues of the Big Bang, including the need for the ad hoc additions of dark matter, dark energy, and inflation. The plenum idea comes from the QSSC, where Nargalar's model had to include a negative energy component in the creation field stresses, which effectively is blowing space-time, the left-hand side, outward from the center of galaxies. That is, the plenum on the right-hand side is a real component of the universe, and its gradient is outward to create the QSS need for a negative energy. So, no infinite curvature nor black hole horizon on the right-hand side. STOE does not use the GR mapping equation. Three arguments that have been used against the steady state model. One is the greater number of radial source galaxies further, that is, say, billions of light years, than near that suggests that the universe has evolved, and this is based on redshift is being a Doppler effect, which we're going to argue with in a bit. QSOs have high redshift, which is taken to mean further away, again suggesting the universe has evolved. Redshift, again, is assumed to be a Doppler effect. And the third is that the CMB, or what they call a cosmic microwave background, is a black body radiation in all directions, assumed to be cosmic. It may not be cosmic. The steady state model has no explanation, but the STOE is going to come up with one. The next 5 slides are from this book by Binney and Merrifield, which is a fairly thick book, and it's fairly detailed in terms of observations. It's an observational book. Okay. we're going to look at what's the difference between elliptical and spiral galaxies, which Binney and Merrifield puts great emphasis on. The great majority of elliptical galaxies are observed to be much poorer in cool gas and hydrogen than spiral galaxies. And there's the page numbers. The bulk of the interstellar matter in spiral galaxies is molecular hydrogen. This is the 22 centimeter line observations. In elliptical galaxies, the bulk of the interstellar matter consists of hot plasma distributed approximately spherical rather than in a thin disk. A characteristic of elliptical galaxies not found in spiral galaxies is that the X-ray surface brightness is nearly proportional to the optical surface brightness. The study of dust lanes suggests the gas and dust are falling into elliptical galaxies and lenticular galaxies and are formed internally in spiral galaxies. That is to say, they're formed internally close to the center of the galaxy and are traveling outward. Some evidence has been presented that suggests irregular galaxies will settle down into being normal elliptical galaxies, and so too also with radio source galaxies. Low surface brightness spiral galaxies, the outer rotation curve generally rises, and we'll see that here in a bit. In contrast, ordinary elliptical galaxies with luminosities close to the characteristic luminosity, and this is an experimentalist number, show a nearly Keplerian decline with radius outside twice the galaxy's effective radius, enclosing half its projected light. The study of gust lanes suggests mass is ejected from spiral galaxies. Galaxies in clusters are much more likely to be elliptical. Spiral galaxies lie further from the center of clusters than do elliptical galaxies. So here then is a cluster structure, which I call a cell. You see spiral galaxies around the outside and elliptical galaxies in the middle. Crudely, the diameter of these things is roughly 10 milliparsecs. In summary, the Big Bang suggests infalling, condensing matter into galaxies. Now, this fits elliptical galaxies, but spiral galaxies reject the Big Bang because they show things flowing out. The QSSC suggests outflowing matter from galaxies. This fits spiral galaxies very well, and many of the analysis that Narklar does in the book, he's talking about spiral galaxies anomalies in the standard model. However, elliptical galaxies reject the QSSC because they have stuff flowing in. The STOE suggests sources, matter flowing out, and sinks, matter flowing in, so the STOE suggests both. I started thinking about the STOE basic concept around 2000. I first applied it to cosmology and astronomy through till about 2009, and then started working on the other end of things, that is, say, the small, which we've already covered. Here we have the universal equation, which calculates the density at any given point. That's this value. It's dependent on sources, source strengths at the center of spiral galaxies, and the strength of the sink in elliptical galaxies. You'll notice that you take the source and then you subtract the mass that's around the source, that is to say, the spiral galaxy mass, and you then have the contribution to the density of rho at some point in space. And this is true throughout all the space. We take the source strengths, and the sink strengths are characterized by the blue band luminosity because that number is available for most galaxies. Now, there's a problem. The B-band luminosity is not all the energy that galaxies put out. So there's a problem which we will address here when we get around to talking about the data of B-band luminosity versus galaxy parameters. Also notice the relative contribution to the universe energy, the plenum density, is slightly different for source galaxies and sync galaxies. And so the universe has a net rho in because of that difference. And that's going to become important when we get around to looking at the cosmic microwave background. You will note that each source and each sync has around it a lot of mass, which is the galaxy that we measure. And that mass has a contribution to the rho here. So a source galaxy is its source at the center minus its contribution from the mass. And of course, the gradient of the rho then produces the force on the rho, which gives you the motion in the rho. The STOE applies the spherical principle, which implies that space has three and only three spatial dimensions. The force that results from the gradient of the rho is the only force, and it's a magnetic force, as we covered in the first presentation. Therefore, the speed of the force determines the time characteristics in the universe, and this is process time. Let's talk about the big now. Now we're talking about galaxies and galaxy clusters. Before we talk about the relations of galaxies, I need to make some speculation about what black holes are, and that's what we're going to cover here. You'll note that this is speculation. Recall what photons and particles are. So here we have an electron structure, which is a structure of hods, and here we have a photon structure. You will note that there's a distance between the hods, and this distance is determined by the rho density in this area, which is determined by all matter, all sources, and all sinks in the universe. This then is a neutrino, and you'll see that you build up structures, as we covered in the first video. We build up structures by a T structure here, which you see here. This is a very strong structure. In the model here, you can take a structure like this and drop it, and it generally tends to stay together. Structures without this T are very weak, and they tend to fly apart fairly easily. Of course, if you do this T structure in a three-dimensional setting, you then end up with electrons and other baryonic particles. In a very high plenum density environment, the distance between the hods decreases, and therefore, if you had then a strong structure in a low rho, you now have a weak structure in a very high rho situation, such as you see here. In my opinion, it's my model. The STOE avoids singularities and infinities by means of requiring the surface force on the surface of a hod. And then you have contact both in causing the rho and in the rho gradient on the hod. There are no singularities and therefore no infinities. Because distance has meaning as only the distance from a hod surface, we have different types of distances between hods that are in a particle and between particles because of the hods in the particles. And they're dependent on the plenum density. Now, the support for this structure comes from a couple of different areas. One is, as we talked about, the Michelson-Morley experiment. Perhaps Fitzgerald was correct. That is to say, because we see that along the sun-moon axis the row density changes, so too then must the length of photons and the size of electrons change with that. And therefore, the apparatus condenses and expands depending on the row, which then is what is being measured. So Fitzgerald suggested this, and that turned into the Lorentz equations, and that is correct for length, but not necessarily for time and that other stuff. As long as the number of hods stay the same in a structure, the mass stays the same also. The second support for what we're going to talk about here comes from gamma ray outbursts from the galaxy center. The galaxy means this capital G here means that this is the Milky Way galaxy we're talking about. And it has been observed that there are periodic gamma ray out. You generally find that they emit radiation pretty much across the spectrum. These gamma ray bursts from the center of our galaxy are without accompanying other radiation. And what the STOE is going to suggest is that is because the very high rho, the very high plenum density next to the source is going to be very high, and that very high is going to compress and therefore loosen the structure of black holes. It's going to essentially cause the black holes to disintegrate, and out comes all these very high gamma ray bursts, gamma rays being photons from the center of the galaxy. So here we have a galaxy cluster. You'll see here that we have spiral galaxies over here, elliptical galaxies here in the center, and spiral galaxies are a source of radiation, which is then leaving. Now, just outside the source, and typically this is within now, the measurement is 12 AU. We have a bunch of black holes inside, say, 12 AU. This is determined by the S stars more recently. And out from that, you then have hydrogen, because by the time you get to 12 AU, nucleosynthesis has happened with the hods in a row, and you now got particles, even hydrogen atoms. And this is verified by shock hydrogen gas clouds that seem to be exiting the area around the spiral galaxy center very rapidly. Of course, between sources and sinks, you've got light and hods, but not all hydrogen leaves. Some of it comes back in, forms denser particles through suns. These suns then turn hydrogen into other atoms, molecules, and eventually they become dense enough so that they have a supernova. A nova explosion does a couple things. One is a lot of the matter that's on the outside of the iron core of suns is ejected as particles, which are heavy elements, and these go over to the elliptical galaxies. Now, these heavy elements, rocks, are falling into elliptical galaxies, and they've traveled some distance, and they're under a force all the way, and therefore they come in very hot, very fast into elliptical galaxies. They're the sinks. They come in so fast that some of them get ejected out again, and this is called a cooling flow, where they eject it out a little ways, and they cool down, they slow down, and then they fall back into the elliptical galaxies, and eventually the matter and the plenum is annihilated in the sink. The other result of a nova explosion, ultimately, is black hole. There are apparently thousands of these black holes, sun-sized black holes, around the center of our galaxy, but outside that 12 AU radius we talked about. And these fall into the center near the source, where they are evaporated out and we start to cycle all over again. The first two of the three arguments against the QSSC model, which we talked about before, depend on galaxy redshift being a Doppler effect. So the first data examination that we want to undergo is to suggest another model for galaxy redshift being due to another effect which can be related to other data sets, such as the Pioneer anomaly, which also in the STOE model is viewed as a frequency shift. First, we have to determine the Ks that we talked about. So we take a look at close to us, and as we go out in a spherical shell, we measure the B-band luminosity ratio for sources and sync galaxies with the distance. And what you see is that as you go away from us, the ratio declines. I mean, we're actually close to a source galaxy, so you'd expect that to be very high. But as we get into the center of our galaxy and we start looking to include other galaxies, you see the ratio declines and becomes relatively steady. Where it becomes steady at is at about 2.718. That's the ratio then. And this is found in this paper. So we substitute that in the universal equation, and here it is. For each one value of whatever, we have 2.718 impact of spiral galaxies. And here we've substituted the gravitational constant for the effect of mass. You note that the plenum density has to be greater than 0 everywhere in our universe. The net rho for a galaxy, as we talked about before, is due to the source strength minus the gravitational mass contributions. This is galaxy redshift, and this data is using Cepheid variable distances. It's called the Key Project data, which is a virtual standard these days of what generated the Hubble constant here. And this is the line that it generated. You will notice we're looking at the redshift as it's measured versus as it's calculated by the equation. The data from here on out to about in there, about 10 megaparsecs away, is in our galaxy cluster. And it's very good. This data corresponds to the tip of the red giant branch, which is about the limit you can do with that kind of a measure, and with parallax type measurements. And the data here is pretty good. However, out here, it isn't so good. This data comes from other clusters, Virgo and Hercules predominantly. Overall, the correlation coefficient is 0.8, which is poor. But this Hubble constant is key in modern cosmology. It's based on very poor relation overall. Now I'm using correlation coefficient. The type of statistical analysis that you do has a lot to do with how you accept data like this. Personally, I would not. I mean, look at these things. They're really way out. And of course, you've got something off. The ones that are in our galaxy cluster, such as Andromeda, have actually a blue shift. So this to me signals problem, but this is fundamental to the understanding of cosmology. And you remember what redshift had to do with the problems that the standard cosmology says with the QSSC. Recall from the first presentation that light or photons is a column of hods. The energy in the spectrum of photons depend on the number of hods in a photon. The plenum density, rho, between galaxies is low, which makes photons very long. The ends of photons are subject to spallation. This is the STOE model of friction, which is where end hods simply are removed from a photon or other particles, which changes the energy or the redshift. The derived equation in the STOE model is this. There are 5 constants, these K's, and these are calculated. The P and all are what's happening to the rho as the light comes from the galaxy to us. There are 5 constants and 32 galaxy data points, so you should be having pretty good data here to calculate. This is a sample of the calculation where we look at the rho at each point from the galaxy to us, and what the rho calculation of all the other sources, sinks, and matter does to the rho. This line and going here is a 1 over r line, and that's what gives you the Hubble relationship. But you'll notice that there are deviations here and here and a little bit here in the straight Hubble relation for this particular galaxy. Here's another sample calculation for a different galaxy. You can see that one. And here you've got a deviation from 1 over r. Here you've got some real deviations here. So this one is going to show a lot of difference from the Hubble relation. But anyway, plot all these things, and what you end up with, the data as taken, ends up with a correlation of 0.88. Still not very good, but still much better than accepted cosmology. And you will notice that we do have a few outliers, where their error curves do not intersect on the line. One of the things I note about these outliers is that they all have a QSO close to their line of sight. Here's Haltenarb's Seeing Red book that he wrote. And if you take the QSOs exactly as Haltenarb says they are in his book, that is to say they are much closer to us than the regular Z value would indicate, and that they are emitted from source galaxies, that is to say we take the distance to be the source galaxy redshift rather than the QSO redshift, and we end up with a correlation coefficient of 0.93. Much better. I started to look at the same thing with elliptical galaxies, meaning radio source galaxies, and there you get into a lot of difficulties because you can't come up with a good distance measure for those things. This is from Haltenarb's book. And here we're wanting to kind of justify what we say about these QSOs. This is Halton. The book has many photographs like this where he's looking at a spiral galaxy here, and this then is a QSO, and he's seeing that, which he's seeing, he says, is a dust lane from QSO to the spiral galaxy, which means that this thing, independent of what the redshift says it is really actually very close to this, which has a much lower redshift. This is another graph that he had where he's looking at a spiral galaxy with a redshift of 0.008 here. And then he's looking at what he calls other QSO galaxies. Here you see 2.3 going to 1.97. And here is a QSO near another galaxy, or at least close line of sight. And you'll notice, like Alton Harp does, is that the redshift of these QSOs starts high, 0.81, and declines as it goes away from the center galaxy. It's another one of Hart's, the origin of QSOs, and strictly speaking, the origin of spiral galaxies. You see what's being suggested here is that the spiral galaxy is a source, and it's emitting not only matter that stays around it, but it's emitting another source, which eventually in time is going to have matter around it. And the reason why the decrease in the Z is because of that negative matter factor. A QSO then has very little matter around it, and therefore it has a high redshift of the source only without the matter. I mean, that's the model we're presenting here. That's the model that Alton Harp presented. Well, this is the data. However, if we take the X factor from the previous equation and plot it, there's their X factor, and there's for the 32 galaxies, which have a distance calculated by Cepheid variables, not by redshift. And we end up with a line. This line looks a lot better overall than what the Key project had, but yet this is still the Key project data. And the correlation coefficient here is 0.93, which is quite good. But the Hubble law here then becomes, with a shift to 110, plus or minus 20. But this factor here in that distance allows for these, which are blue shifted galaxies. Alton Harp suggested what he called intrinsic redshift. He suggested particle masses change on cosmic timescales. Thus, they emit a redshifted light the further you go back in history. You see what he's getting at here. It's very difficult in cosmology to consider this because one of the basic assumptions in doing cosmology is that matter in space is like here on Earth. Therefore, we can take emitted radiation from things far away to be just like it is here on Earth, the spectrum being the same, hence redshift. So, but, you know, I don't like this intrinsic redshift myself, but that's just to report that's what he reported. The STOE suggests the QSOs are young, just like Hart and Harp did. The model is that sources emit mass and some of it stays around the source, thus forming eventually a spiral galaxy. That mass then, as it forms, reduces the redshift that it measures. Thus, the redshift effect is the net of true source strength minus the mass effect. Mature spiral galaxies then reach a temporary balance to emit an amount of B-band luminosity light. This stays relatively same because some of that matter that's emitting the light is going into the center of galaxies, being broken apart, the black holes being broken apart and being re-emitted out. So the O's age is developing more matter. That is, say, lowering the redshift as they develop. This is another observation. It's a plot of redshift, C, versus the number of galaxies with that redshift. And you'll notice it's what's called a periodic redshift here, here, here. And there are some gaps. This is a problem for standard cosmology. Why should they exist like this? Why should there be these periodic redshift amounts? Here I look at the redshift and distance versus angle from, remember what I said, the center of cells. Here is a look in the direction of this galaxy, which is in a cluster or a cell. And we're looking at the measured Z and the distance versus angle as we view it, angle from the diamonds, which are elliptical galaxies. And you see in the center of the galaxy, here and here, the distance as measured by various things appears, well, uniform both sides of the center. In looking at the Z, you see that's not true. It appears as though everything is all bunched up at a given distance. Now, the problem we have is that when you look at that same galaxy is the center of a cluster, and here you see the cluster looks fairly uniform here against our background. So there should not be a grouping of Z or distance, spherical or near spherical, in our view this way. Why is it different along our line of sight? Well, that's because the Z, the redshift, is being influenced differently by elliptical galaxies and spiral galaxies as the light passes by them. The third observational argument against the QSSC had to do with what is called the cosmic microwave background. Now, the STOE is going to suggest that it is not cosmic in the sense that it's due to some very, very far distant radiation, but it's due to the negative feedback flow of the components of the universe, that is to say, the hods. You remember that we had sources emitting stuff, but some of which goes to the elliptical galaxies, all eventually does, but some of it comes back in through black holes, which is re-emitted back out, and eventually everything flows to elliptical galaxies. That is to say, the microwave background that we're measuring is really measuring the temperature around galaxy clusters. So here's how we're going to calculate it. We have a temperature from all time is the total amount of sources and their source strengths minus elliptical galaxies and their source strengths over time. So it's Q in, energy in, minus energy out in the universe. And that is limited to energy in versus energy out of a cluster. We apply the negative feedback principle. That is to say, we imbue the elliptical galaxies with a feedback mechanism. Fine-tuned parameters are controlled by a negative feedback loop. So you have in your home, we hope, a thermostat which controls the temperature. Temperature goes too high, air conditioner turns on, lowers it. Okay. Same thing here. Mass in a sink galaxy becomes too high. The sink becomes too powerful. It drains more energy, more matter and plenum out of the universe than the sources are providing, or vice versa. Sources increase the heat energy in the universe, sinks decrease the heat in proportional to the mass of the elliptical galaxy. This is now simple math, apply the heat equation. This is done in lots of books. And what you end up with something like this. You'll note that in our equation, we determined that the average temperature, that's to say the factor in front of the spiral galaxy factor, was 2.718. That is the hunted temperature, meaning that the thermostat setting. Looking at Penrose in his papers, he's saying that the temperature is actually going down means that the sources have been emitting more, but the elliptical galaxies are sinking more and more and increasing their sink strength. Therefore, the temperature is coming down here. That's the Penrose kind of thing. But you'll note that some time ago, according to this model, the universe turned around and started increasing temperature. That is to say, the sink strengths were low and the source strengths were high, and therefore the temperature coming into the universe was increasing. Increasing temperature means universe expansion. I wonder if in a few years that the James Webb Space Telescope isn't actually looking out into this zone. And why do those galaxies out there look so mature? Well, because they are mature. And they're more than 14 billion years ago when the temperature was decreasing. The communication in standard Big Bang cosmology requires that radiation from one end of the universe be felt at the other end of the universe. This creates then what's called the horizon problem. In the STOE, the horizon problem is solved. That is to say, the radiation that need be effective only be across a cluster, not across the universe. And therefore, the microwave background is being adjusted in temperature, due to a cluster, not due to the entire universe. In conclusion, the STOE explains many cosmological problems, including the Machian model, and it has only 3 spatial dimensions. The STOE cosmology and the quantum scale model support each other.